Good morning students. Today we will find out moment of inertia of solid sphere. Okay. So firstly we will see the keywords. First one is moment of inertia, and moment of inertia depends upon mass distribution. It depends upon mass distribution. Okay. The second one is, you can say, it depends upon the axis of rotation about which you want to find out moment of inertia. Okay. Now another we have solid sphere. Solid sphere means to say it is filled from inside. It is solid from inside. So let us assume that its mass is m and it is of radius r. Okay. So let us see how a sphere look like. You see, this is a sphere of radius r and this is the center. Okay. And we have an axis which is passing through its center, and this center O is also the center of mass. Okay. We are to find the moment of inertia about this axis, x-axis. Okay. And we assume that the mass is uniformly distributed in this solid sphere. Then the volume mass density, that will be mass of the sphere divided by its volume, and the volume of this sphere whose radius is r. You see, this distance from center to circumference, this distance is capital R, this is the radius. So the volume will be 4 by 3 pi r cube. Mass is capital M and the volume is 4 by 3 pi r cube. Okay. To find the moment of inertia of solid sphere, what we will do? We will divide this sphere into disc, various slices. We will cut it like this. Okay. Then you will get a slice. I am talking of this one. Let me represent it with white color. You see, and this slice is of thickness dx along x-axis. This thickness is dx. So I am talking of this distance. This is dx. I am writing it here. This is dx. Okay. And this slice is at a distance of x. Okay. Now you are to think of the shape of this slice. This slice will be of disc shape. This is of disc shape. Okay. And we know the moment of inertia of disc is 1 by 2 mr square. So if we add the moment of inertia of all slices from this point to this point, then we will get moment of inertia of the solid sphere. Okay. So here we are using the trick. We will divide the solid sphere into slices of disc shape. Okay. Now the moment of inertia of a disc shaped disc shaped, I have told you the slice will look like a disc. Okay, so the moment of inertia of disc shaped slice, this will be, let we represent it by di, and it will be dm into r square, okay, divided by 2. Why this formula? Because this axis x-axis is passing through the center of this disc and perpendicular to its surface, perpendicular to surface of the disc. Okay, so moment of inertia about that axis is given by this formula. If we make use of diameter, then the formula will be mr square by 4. Okay, so here this is our case. Now we are to find the mass of this disc. Okay, for that we will make use of a volume mass density. Okay, so here let me calculate calculation of mass of slice. Let this mass is dm and it will be volume mass density into the volume of the slice. Now we are to find the volume of this elementary disc. Okay, for that, you know, this distance is what? This is the radius, and this distance you have taken x, and you have taken this distance which is the radius of the slice, that distance, radius of slice, that is small r. Okay, that is small r. So this small r will be equal to, you will make use of, this distance is small r, this is capital R, and this is x. So here it becomes a right angle triangle where hypotenuse is capital R and this is perpendicular which is small r, and this is base which is x. So you can find the value of r. So here r square will be equal to capital R square minus x square. Okay, so we have calculated value of r square and dm, and in dm you are to find the volume. So to find the volume, what you will do, the volume of this slice will be equal to, you see the thickness of the slice is dx. So if you know the area, and you multiply it with height, the thickness dx, then you will get the volume. Okay, so this volume will be area of the disc will be pi r square into dx. So the volume will be pi r square into dx. Okay, if you substitute its value here and the value of dm in this formula, then you will get the moment of inertia of this slice of disc shaped, that will be, put the value of dm, this is the mass density, value of dm is mass density, into dv, and dv is pi r square, this is pi r square into dx. So now see, this is the value of dm. Now you are to substitute the value of r square. So let me write it r square, because you have r here. So r square it will be r raised to power 4. So I am writing it here. So it will be small r raised to power 4. Clear? Divided by 2. Now you are to put the value of r. You see here two variables are there. If you take this slice here, then the radius will change and x will change. So we have two variables here. One is x and another is r. So we have to eliminate one of the variable. Okay, and for that we will put the value of r square here. Okay, so the moment of inertia of the disc, moment of inertia of the slice which is of disc shape, that will be volume mass density divided by into pi divided by 2. Then you have capital R square minus x square and its square. This is the value of R square, and R square raised to power 2, it will be R raised to power 4. So this is the value of moment of inertia of this slice. Now you are to integrate it to obtain the value of moment of inertia of the total of the solid sphere, and the limits of integration you see. We will start the slices. Thus, if you cut this perpendicular to the axis of rotation, then the slices will start from this point and their size will increase. The maximum size will be here when you cut along the diameter, and then the size will decrease. Okay, and from this point when you move, let this point is A and this point is B. If you move from A to O, x will decrease, and after O, from O to B, x will increase. So the limits of integration will be minus x to plus x. Okay, so now moment of inertia of solid sphere will be I. Let me write solid here, and this will be integration of this di. So you can take the constants out of integration, and here you have pi rho m divided by 2, and if you open up it, okay, one more thing, you have left here dx. Okay, you see dx we have here, so write dx here, and if you open this formula, then you will get r raised to power 4 plus x raised to power 4 minus 2 r square. Then you have x square within the bracket, and you have then dx. So this is dx, and the limits of integration are from minus x to plus x. Okay, and now you are to integrate it. You can see this is even formula, even function. So you can change the limits of integration from 0 to plus x, and you can write here 2. Okay, so if I make that change, then you will get I of the solid sphere. This will be twice of pi rho divided by 2, and the limits of integration will change from 0 to x, and here you have r raised to power 4 plus x raised to power 4 minus 2 r square into x square, and then you have dx. Now you are to integrate it. You see 2 will cancel here. Okay, and let me clear the space so that we become comfortable in calculation. So here you see I moment of inertia of solid sphere about an axis passing through center of mass, that will be pi into rho m divided by, now 2 will cancel, 2 has been cancelled here. Okay, if you integrate r raised to power 4, you see r is the radius, this is a constant, so its integration will be r raised to power 4 into x. Okay, then you have x raised to power 4, and its integration will be plus x raised to power 5 by 5. Okay, and then you have minus 2 r square, and x is the variable, so this is the constant, and you will get minus 2 r square, and x raised to power 3, one power will increase and the same will be in the denominator, and the limits are you see here. What is the maximum value of x? This is the radius. So the limits of integration will be from minus r to plus r. So you are to change it minus r to plus r. So this is one more thing which you need to keep in mind. So here the limits of integration are like this. If you put the value of x equal to r, and after substituting the value of mass density, and the mass density I have told you, this is mass divided by 4 by 3 pi r cube. After substituting these values, you will get moment of inertia of the solid sphere. This will be equal to 2 by 5 mr square. So this is the moment of inertia of the solid sphere. Okay, now if you have the axis of rotation which is passing through, which is along the tangent, you can say, okay, and this axis is, suppose this is CD, okay, then you will make use of parallel axis theorem to find its moment of inertia. So here we have an axis which is passing through the center of, which is passing through a point on the curved surface, and this is CD. So here you will make use of moment of inertia of solid sphere about tangent, about tangent. So this will be I. Here tangent is CD, so you will make use of parallel axis theorem here, and this distance, the perpendicular distance between the parallel axis between the tangent and the axis passing through the center of mass, that is r. So this will be I x, or you can write the moment of inertia about an axis which is passing through center of mass plus product of mass of the body, mass of the sphere, into square of the distance, square of the perpendicular distance between the parallel axis. So here the perpendicular distance is r, so you will write r square. So if you substitute the value of moment of inertia about center of mass, that is 2 by 5 mr square here, then you will get moment of inertia about an axis which is along the tangent. This will be 7 by 5 mr square. You put here 2 by 5 mr square, then you will get the result. Thanks for watching the lecture.